All right, so today we are going to talk about the practical transformer model first. So in a practical transformer, most of the assumptions that we made regarding ideal transformers are no longer valid. So our core permeability is not infinite. We will have some losses and things like that. And so to account for these non-idealities, we're going to have to update our model. So I'm going to draw a simple magnetic circuit here representing a practical transformer. Let me put my core in first before I forget about it. So here is our core. I'm going to wind a wire around this leg like so. This first winding will have N1 turns. We'll have an RMS voltage drop across it, V1, and an RMS current flowing through it, I1. And then for our secondary winding, we'll put that over here on the right. Like so. So we'll have a voltage V2 with this polarity, current I2 with this polarity, and I think this is the color that I'm using for my flux lines. Because we have losses, we're going to have our regular flux circulating around our core like so, but we're also going to include some leakage flux representing some of our losses like so. Actually, I need to update this so that this guy has N2 turns. All right, so we are going to construct a model. And so I'm going to start with an ideal transformer kind of here in the middle. And this is going to be our induced voltage, E1. And over here will be our induced secondary voltage, E2, like so, okay? So it may seem odd that we include an ideal transformer in our practical transformer model, but we need something in there to account for the fact that we were able to step up and step down voltages. And the best thing to take that into account is actually the ideal transformer. All right, so now let's look at things starting from the primary side of our magnetic circuit above, right? So we have a wire that's wrapped around our core, forming the coil on the left that has N1 turns. Wires have resistance. So we are going to start by introducing some resistance here, which I'm going to call R sub P. So this is the resistance of the primary winding, okay? And similarly, there's a wire wrapped around our core forming our secondary winding. So this coil will also have some resistance, which we'll call R sub S. The resistances R sub P and R sub S are what are used to model the copper losses or the I squared R losses in our transformer. So effectively, they're there to represent the conversion of electrical energy into heat, because as we pass current through these coils, they're going to tend to heat up. We're going to exhibit some losses. From our diagram of our magnetic circuit, we can see that not all of the flux that passes through the primary coil links to the secondary and vice versa. This leakage flux is a form of inefficiency in the system, but does not represent a true loss. And so what I mean by that is that it's not actually absorbing any energy or anything like that. And because of that, we're going to represent these losses with reactance, because we know that the average power consumed by a reactance is always 0. So we are going to have some reactance here, J X sub P, and we'll have a reactance here, J X sub S. So this is taking into account our flux leakage losses. And let me extend that wire over like so. So we've taken care of our series components. So I'm going to go ahead and extend this wire along like so, and extend this wire along like so here. We are going to define the voltage drop over here to be our terminal voltage, V1. And we're going to define the voltage drop between here and here to be our terminal voltage, V2. And it should be fairly obvious to see now why our induced voltage E1 is not equal to our terminal voltage V1, and our induced voltage E2 is not equal to our terminal voltage V2 in a practical transformer. Because if we have some current I1 flowing in the primary winding of our transformer, the series resistance and reactance is going to have some voltage drop over it, which is going to change the value of E1. And similarly, if we have some secondary current I2 flowing through our secondary coil, then there's going to be a voltage drop across RS and JX sub S, which will make V2 and E2 not equal to each other. All right, so in addition to the losses that we see in our windings, we are also going to have losses that are attributed to the core. So we are going to have power losses due to eddy current and hysteresis losses that we've previously discussed. And we are going to represent this loss with a resistance R sub C. So what I'm going to do is I'm going to put a shunt path here in the middle. I'm going to have some resistance here, R sub C, that represents my core losses that we've talked about already. And I'm also going to identify a core current IC like so. We also have a magnetizing current that is required to magnetize the core. So we're going to call that current I sub M. And the combination of I sub C and I sub M is what's known as our excitation current, I sub E. So our magnetizing current lags our applied voltage by 90 degrees. And since we have a current lagging a voltage by 90 degrees, we're going to introduce a reactance here, X sub M, that takes that into account, because we know that for an inductor, current lags the voltage by 90 degrees. And so this is our formal practical transformer model that includes all of our various losses that we might see. This can be a little ungainly to use. So now we're going to talk about how we might simplify things. And this simplification is going to come about from referring things from the primary side to the secondary side or the secondary side to the primary side using the impedance transformation process that we detailed looking at an ideal transformer. Okay. So let's start by referring our resistance RS and reactance X sub S from the secondary side of the transformer over to the primary side, or from the right-hand side over to the left-hand side, right? So my left-hand side is going to be effectively the same. So here's my voltage V1. My resistance R sub P, my reactance JX sub P. Here's my shunt branch. Like so. IM, IC, I lowercase e. All right, so how do I reflect a resistance, or really any impedance, from the secondary side to the primary side? Look back in your notes from last Thursday. How do I refer or reflect an impedance from the secondary side of the transformer to the primary side? Yes. Multiply by a squared. I don't think that's right. I think we divide by a squared.
From secondary.
So let's do a quick aside thing here. I could have been mistaken. So if I have an ideal transformer, I'm going to be slightly upset if I redid all my notes for nothing, but that'll be okay. Here's my voltage V1. Here's my current I1. Here's my voltage V2. Here's my current I2. And then here's my generic load ZL, right? So my load impedance ZL is simply the ratio of V2 to I2 based on what the definition of an impedance is. The input impedance seen looking in to my primary terminals is going to be the ratio of V1 to I1. Well, let's see here. So our turns ratio A is defined to be N2 over N1, or V2 over V1, or I1 over I2. So we can see that V2 is equal to A times V1, or V1 is equal to V2 over A. We can also see that I1 is equal to A times I2, or I2 is equal to I1 over A. So V1 is V2 divided by A. I1 is A times I2. So this is going to look like V2 over I2, excuse me, times 1 over A squared, or ZL divided by A squared. So I was right. We divide by a squared. So over here, we are going to have RS divided by a squared in series with JXS divided by a squared. And then we are going to have our transformer. Where, let's see. Since our impedance has been reflected over, right? So that RS in series with JXS has been moved to the primary side. We now just have an ideal transformer over here on the right-hand side without any impedances to really worry about. So if this voltage right here is V2, it's going to be the exact same thing as our induced voltage, right? So I can literally just call that V2 without any loss of information. What voltage would I see across these terminals? Let me go back over here to the relationships that we just ran through really quickly. So the voltage seen on the primary side is going to look like V2 over A. And we are going to call this V2 prime. This current I2 could be referred to the primary side. And so we'll have a current I2 prime that's going to be equal to A times I2. And now, realistically, we don't actually even need the ideal transformer at all, because we know what that voltage and that current is going to look like, right? So, for example, let me do this in a different color here. If I had connected some load impedance ZL across the terminals of the secondary, I could refer that impedance across the terminals of the primary. And so I would have an impedance ZL prime is equal to ZL over A squared over here. And the transformer serves literally no purpose in our equivalent circuit for a practical transformer. It literally does not need to be there whatsoever, which is actually pretty great. Because as long as we can maintain these relationships, we don't even have to think about what the transformer is doing. So this representation where we have simply, let me go down here. This voltage V1 RP in series with JX sub P RC in parallel with JX sub M RS over A squared in series with JXS over A squared let's call this I1. This current is I2 this voltage is V2 over A. This is what's known as the T equivalent circuit for a transformer. We can actually make this even easier. Okay. So let me do something really quickly here. I'm just going to put my excitation current in, my core current, and my magnetizing current. So in most constant voltage fixed frequency transformers, like those used in power transmission and distribution applications, the magnitude of our excitation current, I sub E, is very, very small, usually between 2 and 5% of the rated winding current, I1. So let me write that down real quickly. I'm sorry, what? Oh, yes, thank you. So if IE is very small compared to I1, effectively, that's saying that practically no current flows through the shunt branch. Okay. So it looks as if it was something close to an open circuit, which means that whatever current flows through these guys, practically all of it flows through these guys as well. So we can actually simplify things by just putting those in series. So this is what's going to be called the cantilever equivalent circuit. And that's what we are going to use for all of our analysis. So we're going to have V1 I'm going to put my shunt branch in here on the left-hand side. So here's R sub C, J X sub M. And then I'm going to have a single resistance here, whose value will be RP plus RS over A squared. And a single inductance here, whose value will be, so this will be J times X sub P plus X sub S over A squared. Here's my current I1. This voltage is going to look like V2 over A. And this current is going to look like A times I2. And this is what's known, as I said a moment ago, as the cantilever equivalent circuit, with everything referred to the primary side. We can develop similar models referring everything to the secondary side. So actually, before I do that though, I'm going to call this REQ sub P and XEQ sub P. So this is just the equivalent resistance, series resistance referred to the primary side and the equivalent series reactance referred to the primary side. So if we refer everything to the secondary side, it'll look something like this. So here is our voltage V1 referred to the secondary side. So just to be clear where that's coming from. The voltage on our secondary would just be A times V1. So I'm simply moving that over. Oops, wrong thing. Here. This current is going to be I1 divided by A. We're going to have our shunt branch referred to the secondary side. So this is going to look like A squared RC in parallel with J A squared XM. Then we're going to have our equivalent resistance referred to the secondary side. So this is going to be A squared RP plus RS. Then we have our reactance. So J times A squared XP plus XS. This is our voltage V2. And this is our current I2. So this is the cantilever equivalent circuit. With everything referred to the secondary. We are going to call this resistance REQ sub S and this reactance XEQ sub S. All right, let's use this. So let's say that we have a 20 kilovolt ampere rated 8,000 volt RMS to 480 volt RMS distribution transformer. And it has following resistances and reactances. So RP is 32 ohms, X sub P 45 ohms, R sub S 50 milliohms, X sub S 60 milliohms, R sub C 250 kiloohms, X sub M 30 kiloohms, where these are on the high voltage side of the transformer. We want to determine A, terminal equivalent circuit. Referred to the high voltage side. B, the equivalent circuit referred to the low voltage side. And C, let's actually use this thing for something. We assume that transformer is supplying rated load at 480 volts RMS at a power factor of 0.8 lagging. What is the transformer's input voltage? So effectively, we're trying to find what V1 must be equal to in order to cause our transformer to supply rated power when we have 480 volts across our terminals of our secondary. All right, so first thing that we need to figure out is our high voltage side the primary or the secondary of the transformer? So because we're dealing with a distribution transformer, we talked a little bit about what the signal flow looked like in electric generation network the other day. A distribution transformer is going to be effectively a step down transformer. So it's going to take that 8 kilovolts and step it down to 480 volts, which is a commonly used industrial voltage. So we can read this distribution as just a fancy way of saying this is a step down transformer, which means high voltage is our primary and our low voltage is our secondary. So 32 ohms for RP and 45 ohms for XP are already then high voltage resistance and reactance. Since our high voltage side is our primary and the subscript P is for primary quantities and the subscript S is for secondary quantities. So let's look at some things here. Let me scroll back up. So we are trying to come up with this circuit right here based on the data that we were given. That's what we're trying to do in part A. RP was given to us, RS was given to us, XP was given to us, XS was given to us, RC was given to us, XM was given to us. What's literally the only thing we don't have? A, right? So what should the turns ratio of our transformer be? Since the high voltage side is the primary and the low voltage side is the secondary, then this is going to be the low voltage divided by the high voltage. So that would be 480 volts RMS divided by 8,000 volts RMS, and that comes out to be 3 over 50. From that, the equivalent resistance on the high voltage side is going to be RP plus RS over A squared, which would be 32 ohms plus 50 milliohms times 50 over 3 quantity squared. So dividing by A squared is the same thing as multiplying by the reciprocal of A squared, right? So if I throw this into my calculator, 32 plus 0.05 times 50 over 3 squared looks like 45.8 repeating ohms. Very similarly, XEQ on the high voltage side is going to be X sub P plus X sub S over A squared, where X sub P was 45 ohms. X sub S was 60 milliohms. Multiply this by 50 over 3 squared. And we get 45 plus 0.06 times 50 over 3. 61.6 repeating. And thus, our equivalent circuit would be like this. So let's see. So RC doesn't change. So this is 250 kilo ohms. XM doesn't change. So this is 30 kilo ohms. We're going to put REQ high voltage up here. So 45.889 ohms. And here, sorry, this should be J 30 kilo ohms. This is going to be J 61.667 ohms. So this is what our cantilever equivalent circuit is going to look like with everything referred to the high voltage side of the transformer. Avery, if you want to go turn off whatever light makes this easier to see, you're free to do so. Now you just have to deal with my shitty handwriting, not my shitty handwriting and a glare. Yeah. All right, so any questions about this process? Hopefully fairly easy and straightforward. Okay. So what are we going to do for part B? So realistically, we don't even have to do the same thing, right? So we have the equivalent resistance and equivalent reactant on the high voltage side or the primary side. So we could just refer that to the secondary side directly. How would we do that? Multiply by A squared, right? We're also going to wind up multiplying this guy by A squared, multiplying by this guy by A squared to move it over. So for part B, let's see. So R sub C on the low voltage side is just going to be R sub C times A squared. So that's 250 kilo ohms times 3 over 50 squared. So 250 times 10 to the 3 times 3 over 50 quantity squared comes out to be 900 ohms. X sub m on the low voltage side is going to be, sorry, X sub m times a squared. So 30 kilo ohms times 3 over 50 squared comes out to be 108 ohms. And then REQ on the low voltage side is just going to be REQ on the high voltage side times a squared. So that was 45.889. $165.2 milliohms. And XEQ on the low voltage side will be XEQ on the high voltage side times a squared, or that was 61.667 times 3 over 50 quantity squared. Or 222.001 milliohms. And so we wind up getting this. So 900 J108 165.2 milliohms, 222.001 milliohms, and I need to throw a J out the front there. All right. So now let's figure out part C. So let's scroll back up here so we can see what it is. We are told to assume that the transformer is supplying rated load at 480 volts RMS at a power supply of 0.8 lagging. And we want to figure out what our transformer's input voltage is. So we have a choice to make here. We can either use the equivalent circuit where everything was referred to the primary side, or the equivalent circuit where everything was referred to the secondary side. It literally doesn't matter which one we choose because they're equivalent to each other. So arbitrarily pick primary side. Okay, so let me put our voltages and stuff like that in here really quickly. So this is the voltage V1 that we're solving for. This is our current I1. This current right here should be A times I2. And this voltage here should be V2 over A. And then we have some load on this thing, right? It's operating at 0.8 lagging. This is the voltage drop across our load. This is the current flowing through our load. Which of those two things do we know? This is the voltage drop across our load. This is the current flowing through our load. We know the voltage drop. So the voltage drop on the secondary side was 480, right? So what's it going to look like referred to the primary side? 480 over A, right? So 480 times 50 over 3 wouldn't be a big stretch of the imagination here. 8,000 volts RMS. That's literally the purpose of the knowing the turns ratio, right? So let me go down here to part C, right? All right, so complex power absorbed by our load is going to be 20 kilovolt amperes for the phase angle of the inverse cosine of our power factor, because we were told very explicitly that our load was drawing full power at a power factor of 0.8, right? So that is going to be 20 for the phase angle, 36.87 degrees kilovolt ampere. How would I find the impedance of my load referred to the primary side? So let me go back down here. We're going to play around with the relationships again. This is kind of a review of some of the stuff that we covered in your first power class, right? So if I have a generic impedance ZL, where this is the voltage drop across that load impedance, and this is the current flowing through that load impedance, the complex power absorbed by my load is VL times IL conjugate, right? I also know that ZL is equal to VL over IL. Okay, this is nothing more than Ohm's law. So I could say that my complex power SL could be expressed as VL times IL, where IL is just VL divided by ZL, and I need to conjugate that current. This is the same thing as the magnitude of the voltage drop squared divided by complex conjugate of my load impedance. This is the relationship that we're going to use just for review's sake, though. We could also say that IL is equal to, let's see, so VL expressed in terms of IL. So VL is equal to IL times ZL. So this would be IL times ZL times IL conjugate, which is going to look like the magnitude of IL squared times ZL. So if we had known the current, this would be a way for us to solve for our impedance. Going back. So, excuse me, our load referred to the primary side because that's the decision that we have made is going to be the magnitude of our load voltage divided by the complex conjugate of the current flowing through, excuse me, the complex conjugate of the complex power absorbed by our load. So that's going to look like 8,000, sorry, this should be squared, my apologies. 8,000 volts RMS squared divided by 20,000, so that I'm in volt amperes, angle 36.87 degrees. So 8,000 squared divided by 20,000 with an angle of 36.87. Oops, it should have been negative 36.87. I forgot to conjugate things. I was confused as to why I put it up. 2.560 plus J 1.920 kiloohms. So now that I know what that impedance is, I should be able to use voltage division to figure out what my voltage V1 is, right? So effectively what I am saying, here's my voltage V1. Here's my shunt branch. This impedance literally isn't going to matter at all because it's directly in parallel with the voltage that I'm trying to find. So it's not going to impact my voltage division relationship in any way, shape, or form. I have this resistance, which was, let's see, on the primary side, 45.889. This was J 61.667. And then here is my load referred to the primary side of 2.560 plus J 1.920 kiloohms. And we know that this voltage is 8,000 volts RMS, referred to the primary side, right? So we could say that V1, actually, using voltage division, we would say that 8,000 volts RMS is equal to V1 times 2.560 plus J 1.920 kiloohms divided by 45.889 plus J 61.667 ohms in series with 2.560 plus J 1.920 kiloohms. And from that, V1 is going to be 8,000 volts RMS times the reciprocal of that ratio. So 45.889 plus J 61.667 plus 2.560 plus J 1.920 all over 2.560 plus J 1.920 kiloohms. So I'm going to throw this in my calculator. So let's see. Fraction answer plus 45.889 plus 61.667 over answer times 8,000. Put it in English form. $8,184.46 with an angle of 0.382 degrees volts RMS. So now that we have an equivalent circuit model, we're going to have to remember a lot of the stuff that we remembered or that we learned in our subsequent classes on circuit analysis and all that kind of good stuff, because we're going to use those complex power relationships and all that kind of stuff pretty extensively here. So if there's anything that you don't remember, no, ask first or remember it. That'll work too. But you know, I teach circuits every quarter, so I have most of it up here. I'm not saying I'm never going to make a mistake, but most of the time I should be correct. So just ask about it. We'll revisit things as is necessary. All right. So let me jump ahead a couple of pages so that I'm not going to run into that review thing again. All right. So let's talk about where those equivalent circuit parameters come from. And if I'm not mistaken, Ron, this is a lab experiment that you guys actually do in 361 next year. Okay. So let's label this as determining equivalent circuit parameters. So in order to determine the equivalent circuit parameters of a practical transformer, there are two tests that are performed. One is called the open circuit test, and the other is the short circuit test. Okay? So let's look at the open circuit test first. So typically, the open circuit test is performed let me see, I said on, but by applying rated voltage to the high voltage, oh, excuse me, I got that backwards. Short circuit must be done that way. The low voltage windings with the high voltage winding open circuited. So that'll look something like this. Okay. So this is just my generic excitation source where we are applying rated voltage. And we are going to be measuring the magnitude of the open circuit voltage, the RMS value with a voltmeter. This is going to be the voltage V1. We are going to be measuring the open circuit current with an ammeter. And then we are also going to measure the average power with a wattmeter. This thing right here represents our wattmeter, and it's used to measure the open circuit power. And then now that we have all of our measurement network set up, we'll connect this to our transformer. Where I'm going to call this NHV to let us know specifically. And that's wrong. This is supposed to be the low voltage side. Getting that backwards. And then over here, this will be our high voltage side. That is left open circuited specifically. So let's use the cantilever equivalent circuit to kind of look at what's going on here. Okay, so this is what our test setup would look like. Now we're going to use the equivalent circuit to figure out what parameters that the open circuit test will actually allow us to detect. So for my cantilever equivalent circuit, everything referred to the low voltage side. Here's my rated voltage. We can see, hopefully fairly obviously, that our voltmeter is directly in parallel with our rated voltage source. So that's going to give us the value of our open circuit voltage. Our ammeter is giving us our open circuit current. And then now we have our transformer equivalent circuit model. So here's RC in parallel with JXM. Here's REQ on the high voltage, nope, low voltage side too. Here's JXEQ on the low voltage side. And then we're open circuited over here on the right. So effectively, all of the current that our ammeter is measuring, IOC, is flowing through the shunt branch. None of it flows through the series branch, REQ low voltage plus JEQ low voltage, because it's open circuited, right? So the impedance ZOC is going to be the ratio of our open circuit voltage to our open circuit current, which is going to be RC times JXM divided by RC plus JXM. And using some complex algebra I'm not going to bore you guys with, we'll find that RC will simply be our open circuit voltage magnitude squared divided by our open circuit power. So expressed only in terms of things that we're actually measuring, right? And our magnetizing reactance, X sub M, is going to be 1 divided by the square root of the magnitude of our open circuit current squared over our open circuit voltage. Sorry, square should be out here, minus 1 over RC quantity squared. All of this is under the square root sign. Where these are specifically the values referred to the low voltage side of the transformer. For our short circuit current test, excuse me. So the short circuit test is usually performed by applying a reduced voltage across the high voltage windings such that rated current flows through the short-circuited low voltage windings. So that's going to look something like this. So here we have some reduced voltage. We'll call this voltage V2. We are going to use a voltmeter to measure what's called our short circuit voltage. We're going to have an ammeter to measure our short circuit current. And over here, we have a wattmeter to measure our short circuit power. And then this measurement circuitry is connected to the high voltage windings of our transformer. And the low voltage windings are shorted out such that rated current is flowing through the low voltage windings. So looking at our equivalent circuit diagram, we're going to have something like this. So here is VSC. Here is ISC. This is our equivalent resistance on our high voltage winding. Equivalent reactance on our high voltage winding. Our shunt branch, where this will be A squared RC and J A squared XM. And we short out our low voltage winding. Like so, such that, again, rated current is flowing. So from here, we can see that shorting out our low voltage windings effectively shorts out the shunt branch referred to the low voltage side, so that all of our short circuit current ISC is flowing through the series path. So the short circuit test is going to help us calculate what our series resistance and reactance are. Okay. So ZSC is going to be the ratio of VSC to ISC, which is REQ high voltage plus J XEQ high voltage. And again, using complex algebra, we find that our equivalent resistance is the short circuit power divided by the magnitude of the short circuit current squared. And our reactance is the square root of the magnitude of our short circuit voltage divided by the magnitude of our short circuit current, quantity squared minus our resistance squared. And both of these are on the values that were calculated are referred to the high voltage side. So let's work one last example and then I will end your suffering for today. So let's say that we have a 50 kilovolt ampere, 2400 to 240 volt RMS, 60 hertz transformer. Is tested and the following data is collected. So here is going to be our voltmeter data. Our ammeter data. And our watt meter data. We'll do this in a nice table. So our open circuit test was performed on the low voltage windings. Our short circuit test was performed on the high voltage windings. And we find that VOC is 240 volts RMS. IOC was 6.5 amps RMS. And POC was 65 watts. VSC 45 volts RMS. ISC 20.833 amps RMS. And PSC is 300 watts. And I want us to determine the cantilever equivalent circuit referred to the high voltage side. Of the transformer. So we need to make an arbitrary decision here. Which side is going to be our primary and which side is going to be our secondary? Not at all. It's just, we only need to make this distinction so that if we have to use a squared to refer something from the primary to the secondary or vice versa, we know which number is supposed to go on top. Literally, yeah. Right? So, for example here, all of our open circuit test results are going to give us things that are referred to the low voltage side of our transformer, right? So our open circuit test gives us the shunt branch things. So if we wanted to refer those to the high voltage side, which we are explicitly being asked to do because we want everything on the high voltage side, we need to decide whether our turns ratio is going to be 10 or 1/10. And it just depends on which one we choose to be our primary and which one we choose to be our secondary. The math's going to work out the same way either way, but we won't know which ratio to use unless we establish, hey, this is what I'm considering to be my primary. The transformer doesn't care. So low voltage is primary or high voltage is primary. So the high voltage, if we had N1 and N2, so if the 240 was our secondary and the 2400 was our primary, we would get a turns ratio of 1/10. If we went with the high voltage as our secondary and the low voltage as our primary, A would be 10. All right, so low voltage is primary, high voltage is secondary. All right, so just to be clear here, A is going to be defined as high voltage over low voltage is 2400 over 240 is 10. I'm just going to make a note out here. High voltage is secondary. And we're calling our low voltage as our primary. Okay, so let's calculate our high voltage things from the jump. So let's use the results of our short circuit test, right? So we go back here in the notes. So from the short circuit test, we know that REQ referred to the high voltage side is going to be the short circuit power divided by the magnitude of the short circuit current squared. So going directly from the table here, that's going to look like 300 watts divided by 20.833 amps RMS quantity squared. Throwing that into my calculator, 300 over 20.833 squared going to give me 0.691 ohms. And XEQ on the high voltage side is the square root of the magnitude of the short circuit voltage divided by the magnitude of the short circuit current, quantity squared, minus the resistance squared. So that's going to be the square root of, let's see, so 45 volts. Yeah. Over 20.833 amps squared minus 0.691 ohms squared. I get to be 2.046 ohms. So from our open circuit test, we are going to have RC low voltage. We're going to get some equation. Is the magnitude of our open circuit voltage squared divided by our open circuit power. So our open circuit voltage was 240 volts RMS. Open circuit power was 65 watts. I get 886.154 ohms. So when I refer this resistance to the high voltage side, am I going to multiply by A squared or divide by A squared? So let's go back here and look. So we're going from the low voltage side to the high voltage side. So we're going from the primary to the secondary. So we multiply or divide? Multiply. So that's just going to be 100 times 886.154. So 88.615 kilo ohms. Just move the decimal place over these spots. My reactance on the low voltage side, sorry, that should be X sub M. My apologies. Is 1 divided by square root of IOC over VOC quantity squared minus 1 over RC high voltage squared. That's going to be 1 over, let's see, so IOC was 6.5 amps. VOC was 240 volts RMS minus 1 over 36.154 ohms. And it's cleared. So listen to my calculator. Giving me issues with. No, I should have it. Sorry. Both of these should be low voltage, so that's on me. I'm just having issues inputting it into my calculator, so let me do it in 2 steps. But thank you for finding that area, Bailey. Yep. As would most of you, I'm sure, because it was wrong. 36.154, close parentheses. Clear that whole thing. Take the reciprocal. Open that book here. All right, there we go. Excuse me, 36.955 ohms. And then XM on the high voltage side is just going to be A squared times XM low voltage, or 100 times that 36.955, which is going to look like 3.696 kiloohms. .696 kiloohms. Finally, putting all of this together, our equivalent circuit with everything referred to the high voltage side is going to be, let's see, 88.615 K over here. J 3.696 K over here. And let's go up here. 0.691 ohms in series with J 2.046 ohms. All right. So we've used test data like we might get in the lab. You guys will see next quarter. To get the equivalent circuit with everything referred to the high voltage side. Obviously, if you want to refer everything to the low voltage side, you would just divide all these numbers by a squared. All right, so we only have 15 minutes left of class. I do have 2 more topics that I want to talk about, voltage regulation and transformer efficiency. So we'll knock those out when we get back from the break. All in all, that would take about 45 minutes total. And then the remainder of our class meeting on that Thursday that we get back will be used as a review period. So I hope you guys have a safe and happy break. Spend time with your families, all that kind of jazz. I'm going to post a homework assignment on ideal transformers and practical transformers. It might also have a question regarding voltage regulation and efficiency. I'm not expecting you to answer those yet, and it will not be due until the Tuesday after we get back from the break. So I'm not encouraging you to procrastinate, but I am telling you very explicitly, you will have time after you get back. So please spend time with your family or whoever over the break and don't worry about my crap. So, all right. You guys have a good afternoon and all that kind of stuff. Stay safe.